Have you ever wondered how heat and work are related? It's all about thermodynamics. Welcome to the fascinating world of thermodynamics, a branch of physics that explores the relationship between heat, work, and temperature, focusing on how energy can transform from one form to another. Thermodynamics is a big deal. It's like the backstage manager of the universe, dictating how energy behaves, moves, and changes. It's intimately involved in everything from the expansion of the universe to the baking of a cake. Now let's not get ahead of ourselves. Thermodynamics isn't just one big idea, it's a family of concepts. There's classical thermodynamics, which is all about energy in the macroscopic world. Think steam engines and refrigerators. Then there's statistical thermodynamics, which zooms in to examine energy at the microscopic level. We also have chemical thermodynamics, which looks at energy transformations in chemical reactions. And lastly, equilibrium thermodynamics, which explores how systems reach a state of balance. So thermodynamics is a big deal, and it's everywhere around us. Now that we know what thermodynamics is, let's talk about thermodynamic systems and processes. Picture this. You're a scientist and you've got a certain amount of stuff. Maybe it's a gas, maybe it's a fluid. You want to study it to see how it changes and behaves under different conditions. That stuff you're studying, that's your thermodynamic system. Systems in thermodynamics come in three flavors: isolated, closed, and open. An isolated system doesn't interact with its surroundings at all, meaning no energy or matter can be exchanged. You can think of it as a perfectly sealed box. A closed system, on the other hand, can exchange energy with its surroundings, but not matter. Picture a heated pot with a lid on it. Finally, an open system can exchange both energy and matter with its surroundings. An example of this could be a cup of hot coffee in a room. Now, let's dive into the thermodynamic processes. These are the changes that occur within our system. There are four main types: isothermal, adiabatic, isobaric, and isochoric. During an isothermal process, the temperature of the system stays constant. It's like a warm day that stays the same temperature from sunrise to sunset. An adiabatic process is one where no heat is exchanged with the surroundings. Imagine you've got your coffee in a super insulated mug that doesn't let any heat escape. Next up is the isobaric process, where the pressure within the system remains constant. It's like being at sea level, where the atmospheric pressure stays the same. Finally, during an isochoric process, the volume of the system doesn't change. Picture a gas trapped in a container that can't expand or shrink. These processes allow us to observe and understand how energy changes within a system, whether it's a pot of soup on the stove, the Earth's atmosphere, or even a star in the far reaches of space. So, these processes show how energy changes within a thermodynamic system. Now let's dive into the laws that govern thermodynamics. These rules of the universe, defined as the zeroth, first, second, and third laws, are the foundation for understanding the fascinating world of thermodynamics. First up is the zeroth law, a law so fundamental that it was added after the others, but named zeroth. This law is all about thermal equilibrium. If two systems, say System A and System B, are in thermal equilibrium with a third system, System C, then A and B are in thermal equilibrium with each other. In simpler terms, if A equals C and B equals C, then A must equal B. This law allows us to measure temperature and compare it across different systems. Next, we have the first law of thermodynamics, also known as the law of energy conservation. This law tells us that energy cannot be created or destroyed, only transformed. For instance, when you're cycling, you convert your muscular energy into kinetic energy of the bike. The total energy before and after is the same, it just changes form. Moving on, we encounter the second law. This law states that in any process, the total entropy or disorder of an isolated system will always increase over time. Think of this as a teenager's bedroom. No matter how many times you clean it, it always seems to get messier. Finally, we come to the third law of thermodynamics. This law states that as the temperature of a system approaches absolute zero, the entropy of the system approaches a minimum value. In other words, everything slows down and disorder decreases as things get colder. Imagine a bustling city slowing down and becoming quiet as night falls and the temperature drops. Each of these laws plays a pivotal role in defining the behavior of energy, temperature, and entropy in thermodynamic systems. They help us understand everything from the workings of a simple engine to the complexities of the universe. And these laws are what keep the universe in check. So we've learned a lot about thermodynamics today. We've delved into how this intriguing branch of physics grapples with heat, work, and temperature, focusing primarily on the interconversion of energy forms. We've explored the various facets of thermodynamics, from the classical to the statistical, and from the chemical to the equilibrium. We've journeyed through the concepts of thermodynamic systems, processes, cycles, and equilibrium, all critical to gaining a comprehensive understanding of the field. We've also touched on the fundamental principles of thermodynamic properties, enthalpy, entropy, and thermodynamic potentials. But the real heart of our discussion has been the 4 laws of thermodynamics. These laws, the zeroth, first, second, and third, provide a definitive guide to the behavior of energy, temperature, and entropy in thermodynamic systems. They are the cornerstones that uphold the vast edifice of thermodynamics. And that, my friends, is the fascinating world of thermodynamics in a nutshell.